second. Sorry. Let me try to exit and come back in.
Okay.
Hello.
Hi, Horace. Okay, can you hear me now, Veronica?
Now I can hear you. Yay. Okay.
Yeah.
Good afternoon.
Good afternoon, yes. You know, it reminded me of something when I said, can you hear me now? Decades ago, when I was in my 30s, I was an electronic engineer, and the company I worked for put the satellite GPS system in orbit around the Earth. And it took about 5 years to launch 24 satellites into space. So beginning in the mid 1980s, all of those satellites had to be calibrated, you might say. This is going to sound totally nerdy, but some of Einstein's theories really did come into play. And what that means is those satellites are in outer space and they're in a zero gravity environment. That means time moves faster for them. So all of the clocks on the satellites, we had to take into account that discrepancy between the timing of the satellites and the clock that's located in your phone. And it took about 5 years to calibrate all those satellites. And so for about 5 years, I did a lot of traveling. And basically I was saying, can you find me now? Can you find me now?
Professor, I have a question.
Yes.
I never received my grade, and I send you a couple emails, and I didn't hear from you.
Let me see here.
It's
Lily?
Liliana. Yeah, Liliana Galvez.
Let me see my roll sheet here. Lily, I'm not seeing you on my roll sheet.
What?
Were you here on the first day of the week?
Yeah, I've been every Zoom. I've been here.
Okay, because I don't have you anywhere on my roll sheet. Okay.
No.
I will double check that as soon as we finish class here to see whether or not you're officially enrolled in this class. But because you're not on my roll sheet, dear, that's probably why you were not receiving any messages from me, because I don't have your email address.
But I do get everything from you. Like I got the text, I got the emails, I got everything, but.
Let me have, can you, would you mind what's your email address?
You could do, well, the one from here is LCAS. Let me double check, because I'm not even sure.
Okay. Well, I'll tell you what, when we finish here, you have my Tuscan Med address, correct?
Yes.
Okay. Why don't you send me a message, and that way I'll be sure that I have the correct email address for you.
Okay.
And I will look up my census in administration and find out whether or not you are officially enrolled in the class or not. And if you're not, well, obviously we got to take care of that. So, but I'm just letting you know right now, your name's not on the roll sheet, but we'll look into it as soon as I get done here.
Okay. Yeah, because I've been getting all your emails. Like I've been printing out all the everything that you send. I just print out everything that you sent today.
Oh, wait a minute. You're under I think I just found you. You're Castillo de Galvez,
Yes.
not Galvez.
No,
Castillo
Castillo.
de Galvez.
Yes.
Okay, that matters, dear.
Sorry. Sorry.
Okay, just FYI, future reference, that matters. Okay. You are correct. I did not receive an answer sheet from you, and
What? I sent it
I
to you
did.
twice.
Okay.
My God.
Don't go into a panic, dear. We'll find it. Okay.
Okay.
I'll do a search in my own inbox and things like that, because something that I have discovered, and all of you should listen to this in case there's an issue sometime in the future. And I cannot explain why this happens, but on occasion, when you send me a message, and I'm sure this happens in reverse when I send you a message, somehow that message gets linked to other students' addresses.
Oh, wow.
So when I receive the message, it's under somebody else's name. And your original message is somewhere in that file.
Oh, wow.
I don't know how that happens. And I'm sure it's probably happened when I send you a message and I somehow get linked to another student's name, and you're not aware that the message was from me.
Okay.
So that's why I'm not stressing a whole lot over this, Lily. We'll find it.
Okay. Thank you.
Uh-huh.
I received your email about that you had sent our grades, and I went and checked, and I was like, So I emailed you right away, and since I didn't get a response yesterday, I'm like, okay, let me try again. Maybe he was busy, work.
We'll find it.
Okay.
Yeah, most of the time I can find it when I do a search specifically for your name.
Okay.
And like I said, I know that sounds really strange, but you know what? Ever since we started doing this online stuff, what was it, 3 semesters ago?
Yeah.
Essentially, and I know it's really inconvenient for pretty much all of you students, but it's, for me personally, it's like trying to teach an old dog new tricks. And I'm just like, I am so done with this.
I am too, Professor. I cannot lie. I do not like online classes.
Oh, you're preaching to the choir, girl. Yes. Yes. And the sad part is that even when we go back to class, or when you go back to class, they're going to limit enrollment in the classes so that they can space you apart. They're not, from what I'm hearing, classes that would normally have 50 students in it are obviously going to be cut down to, say, 25 or 30 students because of the seating arrangements. So if if there's a class that you really need, you need to jump on it right away, because these classes are going to fill very quickly. And who knows how long that's going to last, And then the big $64 question is are you going to be required to wear a mask while you're in class? I don't have anything against masks personally. It's just sometimes it gets a little stuffy. All right. Okay, everybody. I think everybody's here that is planning on it. So let me get started here.
Recording in progress.
Okay, as promised, everybody, I'm going to go over the answers to exam 1 real quick. Unless there's, which I'm not anticipating, I don't have time to go over each of the questions with you. I'm sorry. So I'm just going to go over the answers right away. And that way you can at least double check your own, see what it was you possibly missed. So number 1, that was 9 hours. Question 2, that was the Great Circle Path. 3 was either matter and or energy. 4, that was a positive feedback loop. And number 5, those were parallels. Okay, question number 6, that was the letter D as in dog. 7 was also D. 8 was A. 9 was B as in boy. And 10 was the letter C. Question 11, let's see here. That was the letter B. 12 was E. 13, 14, and 15 were the letter C. 16 and 17 were false. 18 and 19 were true. Number 20 was false. 21 was true. 22 was false. 23 and 24 were true. 25 was false. The matching, just going to read through the letters really quick here. M, O, J, L, Q, C, R, I, B, F, K, N, A, P, H. Now, beginning with number 41, D as in dog, A, C, E, G, B as in boy, J, H, F, I. Okay. Overall, the class did really well. I kind of expected that, but at the same time, just a little FYI here, everybody. Some of you are considering maybe even graduate work down the road at some time. And yes, your GPA matters. It does. But if you're a true bona fide, say 3.6, 3.7 student, it says something else about you personally besides the fact that you can pass tests efficiently enough. It also says something about you as a student. You know how to manage your time. You know how to prepare for exams. You know how to comprehend new material. So keep that in mind, everybody. If you're a true 3.6 GPA person, there's more going on than just being able to pass tests. So anyway, okay, exam 2 material. Oh, one more thing before I get started on exam 2, everybody. I have to insist for exam 2, please use the answer sheet and return the answer sheet to me. A couple of you wrote your answers on the actual test itself and returned the entire exam back to me. That's an awful lot of paper to print out. And some of you used highlighter pen, and that doesn't always translate to a printer. So I have to actually pause and read your exam on the computer to correct it. So please, everybody, use the answer sheet, okay? Anyway, to begin with exam 2 material, I want to make some preparatory comments first before we begin, because if you've had time so far to print out the handouts that I sent earlier, about an hour ago, everybody, it may come across as intimidating to some of you, like, oh my gosh, what are we getting into here? So I want to calm some of your concerns over this, if they do exist. And yes, the topic itself is not complicated. Everybody in this class is perfectly capable of understanding it. The biggest issue, which I think you're missing here, it's new to you. That's it. It's new to you. It doesn't mean you can't understand it or learn it. It's just new to you. Keep that in mind, everybody. You do have the ability to understand the science. You know, don't be afraid of it, okay? I am not going to require you to perform any math on exam 2. So there's going to be some problems presented in the handouts that I gave you. And some of those actually say quiz on them. No, you are not required to turn anything into me. I will go over this. However, they're also practice exercises for you. You do not have to turn anything into me, okay? But I will explain them. And if some of you want to participate at home on your own and try to solve some of these little problems that I'm going to show you in there, then by all means, please do. And if you have questions, you know, you can always message me, and I'll be more than happy to explain whatever the issue is that you're having with the problem, okay? So when it comes to exam 2, everybody, no, you are not going to see those problems on the exam, okay? You're not going to do any math, okay? I might possibly offer it as extra credit, but it won't be on the exam itself, okay? So I'm looking at the study guide, everybody. And underneath where it says solar energy and Earth's atmosphere, essentially this first section of material here is dealing with our relationship with the sun, specifics about our relationship with the sun, okay? Our exact position in relation to the sun is obviously very advantageous for life. If we were too close to the sun, all the water on the surface would literally vaporize and disappear. And if we were too far away, it would literally freeze. All the oceans would be solid. So we are at what astronomers call the Goldilocks zone. We're in just the right distance from the sun to keep water liquid. We like liquid water, okay? So this section of material in the very beginning deals with some of the specifics of our relationship with the sun. And it starts with the topic, if you look on the study guide, it says fusion. I think a brief explanation of this process. However, all I really need you to know for the exam, everybody, is that fusion is the joining of two atoms. That's all you need to know. But I had mentioned this during exam 1 material. When the solar system formed, it was essentially a big, huge dust cloud. It spun itself into a disc, much like a lump of pizza dough gets spun into the shape of a pizza. And most of this dust is going to end up in the sun. And the sun, our sun, is approximately 1 million miles across in size. Remember, Earth is just under 8,000 miles across. Well, the sun is nearly 1 million miles across. So it's a very large object, and all of that gas that has accumulated in our sun, everybody, is creating a tremendous amount of pressure on the very center of that sun. The gravity is so intense, everybody, that the temperatures in the middle of our sun are in the 18 to 20 million degree range. And as it turns out, everybody, when you heat hydrogen up to those temperatures, the individual atoms of hydrogen are moving around so rapidly. And because there's so many of them, what are the odds that two of them are going to randomly collide with each other? Well, because of the intense pressure and the intense temperatures, that's going to happen frequently. And when you do that, you get the big kaboom. Okay? So it's releasing energy that is pushing outward against all of the gravity that wants to crush it down to nothing. So there's this happy balance that has happened over time, a happy balance between the amount of energy coming out of the interior of the sun against the gravity that wants to crush it down to nothing. We've been able to calculate how much of this hydrogen is in our sun. There's quite a lot of it, as you might expect. However, be happy to know that the gas tank is still about 3/4 full, despite the fact that it's been burning for nearly 5 billion years. So this section of material deals with, okay, fusion is the joining of two atoms, but this part of it deals with what is being released, what's being created. That's what this section deals with here, because it's this material that is eventually going to escape into outer space. It's going to strike Earth's magnetic field and its atmosphere, and a portion of it is actually going to strike the surface of your skin. So in this material here, the letter B underneath fusion, everybody, it says electromagnetic waves and the electromagnetic spectrum. In the handouts that I gave you earlier, everybody, there are diagrams that show you what I'm talking about, okay? Let's see here. One of them looks like this, okay? We do have the technology to look at electromagnetic waves. It's a common technology. We've had it for well over 100 years. We've just improved upon it, as you might expect with modern technology. So we have a better understanding of what exactly it is the sun radiates out into space. Now, it's a large ball of gas And so it's radiating its energy in a 360-degree pattern, okay? And the energy that it's radiating is what we call a broad range or a broad spectrum of energy. And there's a concept that you should or need to understand if you're to understand this topic of electromagnetic waves. Of all the energy that the sun puts out into space, everybody, and it puts out a lot. It puts out radio waves, it puts out sound waves, it puts out X-rays, it puts out microwaves, and it puts out visible light. Okay? As it approaches Earth, everybody, most of what the sun puts out into outer space is bad for life. And I'm talking about X-rays and things like that. I mean, you don't want to be exposed to X-rays for a very long period of time. If you've ever been to your doctor's office or possibly your dentist and they took a picture of your teeth, did you notice that the X-ray technician stepped out of the room when they took the picture of your jaw? And were you aware that the machine was actually only on for less than 1 second? Because you cannot be exposed to X-rays for any length of time. So they want to minimize your exposure to it. And of course, the technician steps out of the room because you're probably one of a dozen different people they took a picture of. And of course, they don't want to be in the room every single time when they do that. So they step outside. But there's a reason why these are bad for you. Okay. And it's in the diagrams that I provided you in the handouts that I sent you. Electromagnetic energy, everybody, if you looked at it on a piece of equipment specifically designed for this, you would see what looks to you like a sine wave. Now, a sine wave is something some of you, if you have any kind of math background, everybody, sine waves, you're typically first introduced to them in your very first algebra class. Okay, so if you've had algebra or possibly higher math classes, then you're familiar with the concept of sine waves, okay? But for those of you who are not familiar with this, I've provided you some diagrams and some explanations there, okay? Some basic concepts I want you to understand. When the sun radiates this energy out into space, everybody, it's referred to as solar energy. It moves through space at the speed of light. Therefore, when this energy leaves the sun, the distance to the Earth is 93 million miles. We've already talked about this. It was an exam 1 question. It takes solar energy 8 minutes to reach Earth. That's fast. When it reaches Earth, Earth is surrounded by a magnetic field. The planet Earth, everybody, is essentially a huge magnet. And I'll explain that later, but it's a huge magnet. And therefore, it is surrounded by magnetism. And it's that magnetism that blocks most of the solar energy from actually striking the surface of the Earth. A little bit gets through. And then, of course, our atmosphere also provides some degree of protection, not as much as the magnetic field, but the atmosphere does. What ends up hitting the surface of the Earth is a little bit of the infrared. You know that as heat. All of the visible light, and a little bit of the ultraviolet. That's a very, very small portion of the entire electromagnetic spectrum. A quick example of the electromagnetic spectrum of itself, everybody. You've been listening to me speak to you now for a couple of weeks, so you've at least gotten used to the sound of what I perceive as my nasally voice. I am speaking to you most likely at a frequency somewhere around 500 or 600 hertz. If you look on the diagrams, I said that I showed you a picture of a sine wave, a single sine wave. And it was located between two bars. And I said solar energy moves at the speed of light. And the speed of light is 3 × 10⁸ meters per second. Translated to common American usage, everybody, that translates to 186,222 miles per second. That's fast. So everything is referenced to 1 second of time, because that's how fast light moves. And all electromagnetic energy moves at the speed of light. So there's one complete waveform in there. And therefore, because there's only one of them, it only has a frequency of 1 hertz. You can squeeze all 600 hertz of the sound of my voice into the same time frame of 1 second. Do you see that if you were to put 600 waveforms within a 1 second time frame, each individual waveform is going to get shorter and shorter? Do you see that? But you got to go even higher, everybody. For you ladies in the classroom, it's natural. You speak with a slightly higher pitched sound than we men speak in. So if I were to look at the sound of your voice on a spectrum analyzer, many of you ladies are probably speaking in the 600 to 800 hertz range, a little bit higher than we men. So you're going to squeeze 800 of those waveforms into the same 1 second time frame. But hell, you haven't even gotten started yet. You've heard that dogs can hear sounds that humans cannot hear. Dogs have a known ability to be able to hear up to 100,000 hertz. So you're going to shove 100,000 of those individual waveforms into a 1 second time frame. The length of the individual sine wave is getting even smaller. But still, we're not even close yet. You go up higher and higher and higher. And I'm going to jump leaps and bounds here, everybody, because we don't have a whole lot of time. But for instance, the city police officers, when they talk on their radios in their car to their central dispatchers, they're doing so at a frequency of around 450 megahertz, which is 450 million hertz. You're going to shove 450 million of those individual waveforms into a 1 second time frame. The length of the individual waveform is getting incredibly small. But you still have to go higher. Your cell phones are operating at frequencies between 800 and 900 megahertz. So there's 800 million of those individual waveforms crammed into the same 1 second time frame. And so you can well imagine the length of an individual sine wave is so small, everybody, that we collectively refer to this section of the electromagnetic spectrum as microwaves. But you got to go up even higher, everybody, because we have not reached visible light yet. You go up a little bit higher now, let's say you're in the 10 to the 10th power range. Now you're in what's called radar. The police officers that use those handheld radars to clock you for your speed, they aimed a gun at you. And instead of shooting bullets, it was shooting a wavelength at you that was in the gigahertz range. And so when you go to buy those electronic speed detectors at the electronics store, you know, the ones that light up when they, you know, when the police are using their radar, I think those little devices are absolute scams. If you think about it, everybody, if that little red light comes on, it means you've been caught. Oh, well, anyway, so the individual wavelength is getting smaller and smaller and smaller. So I'm jumping way ahead here, everybody, because again, we're short on time. I'm going to go all the way up to 10 to the 14th power. You can imagine that the individual wavelength is really, really, really small. When you get up to 10 to the 14th power, everybody, you're starting to enter the range known as infrared, and you are beginning to enter into what's called visible light. Visible light runs between the frequencies of 10 to the 14th power up to 10 to the 16th power. Your eyeballs can see that frequency. Your eyeballs are essentially the electronic equivalent of an antenna. And instead of listening to music on AM, FM radio, your eyeballs are specifically tuned to see light. Have you ever noticed when you watch a science fiction movie that aliens typically have the ability to see heat? Well, they must have grown up on a planet in which the only form of energy that got to the surface was infrared or heat. So their eyeballs had to adapt to seeing heat. And in our case, we've adapted to seeing visible light. Now, this is not a test question, everybody, but there's a real easy way to remember all the colors in the rainbow. It's a mnemonic that we used to use in the world of electronics. I think they still use it. I haven't worked in the business in a long time. But if you want to remember all the colors in a rainbow, everybody, there's a mnemonic that goes, bad booze rots our young guts, but vodka goes well. That's every color in the rainbow. If you look at the diagram for the electromagnetic spectrum that covers visible light, everybody, bad booze, that's black and brown. Rots our young, that's red, orange, yellow. Guts, Bud vodka, that's green, blue, violet. And goes well is gray and white. Now, do you notice that when you go from infrared toward ultraviolet, you are increasing in frequency. You're going from 10 to the 14th up to 10 to the 16th power. The size of the individual waveform is incredibly small. So as you go from infrared towards ultraviolet, the wavelength gets smaller and smaller and smaller and smaller. When it comes to human flesh, everybody, really small wavelengths are very bad for us. And let me give you a quick example of what I'm talking about. I said that Earth, between the magnetic field and our atmosphere, I said a little bit of the ultraviolet penetrates and reaches the surface of the Earth. There's a difference between ultraviolet and infrared. Infrared you perceive as heat. Now, most of you have stood in front of a fireplace or a heater at one time in your life. You were cold, you wanted to get warm, so you stood next to the fire. And as you stood next to the fire, you got warm and eventually got to the point where, all right, I'm done. I'm warm enough. It's getting uncomfortable. So you stepped away from the fireplace. And I've already explained this to you. I know I have. And your body began to give that heat up. But my point is that you were able to stand in front of that fireplace and absorb some of that heat and feel good about it. And then after you stepped away, it would re-radiate back out into the room. You can't do that with ultraviolet, everybody, and here's why. Ultraviolet is a much, much, much smaller wavelength than ordinary heat. It is small enough, everybody, that as far as your skin is concerned, the ultraviolet, it's like Swiss cheese. It just passes right through you. The risk you take when you sit out at the beach to get a suntan is that what are the odds that some of that ultraviolet, because ultraviolet is what gives you the sunburn at the beach, not infrared. It's not the heat itself at the beach that causes your skin to turn red, everybody. It's the ultraviolet that is penetrating the atmosphere and striking your skin. The danger comes from the fact that this wavelength is so small, everybody, that it actually is able to penetrate the cells of your body. If by random chance it happens to strike the nucleus of that cell and damage it somehow, as the cell attempts to reproduce itself later on down the line, it will not be able to reproduce itself in an exact copy, which is what it is designed to do. And when that starts to happen, if it's happening to numerous cells at the same time, we call that cancer. Ultraviolet actually contains more energy than infrared or heat. The danger is that because the waveform is so small, you don't feel it so much on your skin, do you? What you feel is the heat itself, which is the infrared. What you are missing is the fact that the ultraviolet is completely passing through your skin, and the energy is being transferred to the cells of your body. Infrared or heat, the wavelength is longer, and so it doesn't penetrate your skin as easily, so it transfers its energy right onto your skin and you feel hot. You feel that. What you don't feel is your cells being disrupted by ultraviolet light. Have a good day at the beach, everybody. You know why you put tin foil in your windshield at the parking lot in your car? Infrared is going to, it's small enough, and that entire visible light spectrum, it is small enough to pass through the windshield of your car like it's not even there. And as it passes through the windshield in your car, everybody, it's going to pass through the cloth or the pseudo leather in your seats of your car like it's not even there either. However, it's going to come into contact with the metal springs under your seat. Now, the metal is much more dense, so the energy is going to be reflected back towards the windshield from these metal springs. The problem with it is I'm making a connection here, everybody. If you look at the diagrams, it says there's a relationship between frequency, wavelength, and energy. What I've been talking about so far is increasing frequency. We went from the sound of my voice up to visible light, and frequency increased. When we went from my voice up to visible light, the size of the individual waveform got shorter and shorter. What I have not mentioned yet until now is that from the sound of my voice up until visible light, or actually up until infinity, but as we got to the visible light, everybody, the energy content of the waveform increased. Here's an easy way to remember that, everybody. Do you remember red is on one side of the color spectrum and the color white is on the other side of the color spectrum? Red is located near infrared or heat. White is located near ultraviolet. So I ask you, what is hotter, red hot or white hot? Easy way to remember. So as you go up in frequency, the amount of energy in the waveform increases. Likewise, because the size of the individual waveform got shorter and shorter as you went up, shorter wavelengths are very high energy. This is why ultraviolet is so dangerous to your skin cells. It's transferring that energy to your cells. And this is also why the X-ray technician steps out of the room, because X-rays are at the 10 to the 18th power. That's an incredibly small waveform. And this is why, for you ladies who've ever had children, you did not get an X-ray, did you? They did a sonogram on you, because the fetus, it's going to transfer its energy to that cell. Not good, not good. Yes. We are all susceptible to ultraviolet, some of us more than others, and I am one of those. And it's precisely because I am Caucasian. My body does not tolerate, I shouldn't say my body, my skin does not tolerate as easily as, I don't have no idea what you look like, Jack, but I'm assuming you're Hispanic. So your skin better tolerates the sunlight than mine does. So yes, I recently discovered something on the internet. There's a company out there that makes t-shirts, everybody. They block ultraviolet light so that you don't have to put on a bunch of that goopy sunscreen. So you should look those up, everybody. They've got these UV t-shirts that are really cool. But anyway, this is also, everybody, side note, this is not testable material here. I'm going off track for just a little bit because we're getting close to the end here. I want to show you or demonstrate to you how we use the visible light spectrum in other aspects besides looking at things. You have the ability to see. So when we say that, it means you can see the visible light spectrum. So you can see the color red or blue or yellow or something like that. But if you look at it from the point of view of science, what you're looking at is the frequency of the color red versus the frequency of the color white and what that all means. So in the world of astronomy, everybody, the one end of the color spectrum is collectively referred to as the red end. And the opposite side is collectively referred to as the blue side of the color spectrum. So are you all familiar with the idea in science that if you stood on a street corner and you heard an ambulance siren coming at you, didn't the pitch of the siren appear to increase as the ambulance got closer to you? It got louder and it got a higher pitch, right? After the ambulance passed by you, the sound of the siren, it appeared to get duller and duller, because it was fading away. You can use that same concept when you look at stars through a telescope, because when I explained the ambulance, when the sound of the siren was coming at you, it sounded as if the pitch of the siren was increasing. And in a way, yes, it was. Even though the siren itself was always pulsating at the same frequency. But why did it sound like the pitch was increasing? Because the sound was coming at you at a certain frequency. However, because the siren was physically moving toward you, it was squashing those wavelengths and it was making it sound like it was a higher pitch. When it passed by you, the sound of the siren appeared to get lower and, like I said, duller, because it was moving away from you. So the size of the individual waveform got longer. When we look up at stars in the night sky through a telescope, everybody, it's real easy to tell if it's moving toward you or moving away from you. And it's called the red shift or the blue shift. Because if the object is moving away from you, that means the wavelength is getting longer, and that's the red end of the color spectrum. If the star or the object you're looking at is actually moving toward you, then the light is going to be squashed. And that's the blue end of the spectrum. So that's how they tell what directions objects are moving in when they look up at the night sky. They take the concept of a sound that appears to increase in pitch. Well, light does the same thing because they're all electromagnetic waves, sound waves, X-rays, microwaves, gamma rays, ultraviolet rays. They all are. And the sun radiates all of this into space at the same time at the speed of light. When astronauts go up into orbit around our Earth, everybody, they have absolutely no protection from those cosmic rays that are being radiated from the sun because they are outside the limits of our magnetic field. When Neil Armstrong landed on the moon back in 1969, everybody, he may as well have been standing in front of a microwave oven set to high heat. I mean, it was there was no protection between what the sun had to put out, and the only protection they did have was those flimsy spacesuits they were wearing back in 1969. That was it. So whenever the astronauts came back and landed down on Earth and they went through their physical exam, nearly every one of them reported a phenomenon that was, it's now common. We understand what it is now, but it's common occurrence. Some of these cosmic rays will actually pass through your body, everybody, and occasionally one of them will pass through your eye and it will hit your optic nerve, and you will have the sensation of a flashing light passing through your eye. It almost to you looks like a shooting star almost. But, you know, in reality, you didn't actually see anything because you're looking around looking for this shooting star, but it's nothing. What it was this cosmic ray striking the nerves in your eye, because they've got no protection up there at all from the sun. So the sun's cosmic rays that it radiates, everybody, are powerful enough that the planet Mars has a very, very weak magnetic field. Literally, you might consider it this way: all those cosmic rays, consider them collectively referred to as the solar wind. This is all the energy the sun puts out into space. That solar wind is powerful enough, everybody, that it blew Mars's atmosphere clean off the planet. It's pretty strong stuff. And so you should thank your, excuse the joke here, lucky stars, everybody, that we are in fact surrounded by a magnetic field that helps protect us. So without that magnetic field, everybody, there is just no life, period. None, not even plant life. We'd just be a bare rock. Because without the magnetic field, everybody, the solar wind would blow the atmosphere clean off Earth. It may take it 1 million years to do it, but it would do it. Anyway, I'm going to conclude with that because I understand this material might have been a bit overwhelming to some of you. So I'm hoping you'll be able to develop some questions about this by tomorrow, or possibly message me later on. And Lily, I will look up your test for you, okay? So if anybody has any questions, I will see everybody tomorrow.
Thank you.
Mm-hmm.
Thank you.
Bye.
Recording
I have a
stopped.
question. I have a question for you.
Yeah.
All right. Okay. So I went through the test with you, and I was going to ask you about number 1. Okay. So you said the answer was 9 hours, but number 1 asks 9 hours of time is equal to blank
135 degrees. I took 135 degrees.
Yeah. Okay. So you took that one. So I was just wondering, because when I was going through, each of them was worth 2 points, right?
Yeah.
Okay. So I got a 96 on there, but I only got 1 wrong.
I will double check it, Christy.
Okay. I just wanted to make sure. I'm very stingy about my grades. I just want to let you know I have a 3.8 GPA, and I'd like it to always stay that way.
Okay. Fair enough. Fair enough.
Yeah. So yeah, the only one I got wrong actually was number 8. And I can see where I erased the correct answer because I double, I thought it too much.
You second guessed yourself.
I second guessed myself. That's what I was looking for that word. But anyway, so I actually got it right the first time, but then I changed it. So number 8 was the only one I got wrong.
Okay.
So
fair enough.
All right.
I will look it up.
Okay. Thank you.
It was the same thing for me. I only missed 2, but I got the same thing as her.
Oh my God, I got 2 of those students.
I'm super stingy. I check everything. I read everything.
No, actually, I mean, I hope you don't take this personally. It's just that I do admire your tenacity in this, because what is sad is most students don't keep track of their points or their grades. They don't.
Mm-hmm. Oh, I learned from having Mr. Swisegood. So I had him for 3 years. So
okay, fair enough. Yeah, because it's a source of amusement to me. Students will approach me at the literally like the last week of class, They have no idea how many points they have. They have no idea that they're, even if they scored 100 on the exam, they'd still fail the class. And they actually show up to take the exam thinking that I'm somehow miraculously going to save them and pass them. And it never fails. So when I meet students like yourself who are fighting for that one extra question, hooray, you guys do it.
I'm really sorry I'm that way too.
I'm not.
You shouldn't feel sorry about it. You shouldn't feel bad about it.
When I had emailed you and I had asked you, well, what questions did I get wrong? Because I just want to know. So I know, and you're like, are you one of those students? And I was like, I'm sorry.
No,
that's okay. I'm with you, girl.
No, like I said, I admire you guys' tenacity because unfortunately, you guys are the exception, not the norm.
Well,
Yeah.
see, this is my second time around in college. I changed careers. And so my first time in college, I was a little bit younger and very young and boy crazy. And I let my grades slide at my old college in Stockton. And now as an adult, older adult, I'm like, okay, so I've had all straight A's, some B's, but then my grade point average from my old school has brought my GPA down. So I'm like,
Caught up with you, didn't it?
So every little bit, I'm like, I want an A if I get it. So
you know
yeah.
what? That's, actually, that would be a good lesson, Veronica, for some of the younger students in the class, because when they blow off classes and they get the Fs, it never goes away on their transcripts. And you found that out. And it chased you down, didn't it?
It sure did, because at COS, I should have a 4.0, but I have a 3 point something. So
because of that, yes.
yep, because of that.
But you know what though? I mean, I've been teaching at COS since 1998, and traditionally over the course of all those years, statistically, my best student has always been women in your category, young moms, either single or married, but young moms. And you're probably working a job, you're going to school. And so that makes you very focused. It makes you very aware of your time management, obviously. And you may not like geography, you may not like whatever class you're in, but you're going to do what it takes to pass the class. And most of the time, these students are the ones who, get the best grades in the class. So you're in a good group of students, statistically speaking. So whatever it is you're doing, keep it up. Don't change it, and keep fighting for that extra question.
Thank you.
2 extra in my case. I'm just saying.
Okay. I will look them up.
All right. I appreciate it. Thank you.
Bye-bye.
We'll see you.
Mhm.